In this video, I would like to talk about household heterogeneity. Now, in an earlier video, we talked about household heterogeneity using the framework of an overlapping generations or OLG model. However, those models are useful mainly for thinking about life cycle issues, such as retirement. The point is that there are plenty of other frameworks for thinking about household heterogeneity that don't necessarily require the use of overlapping generations models. So I thought it would be useful to go through a few examples. Now my first example is going to be the Huggett 1993 model, which is a simple model with incomplete insurance. So what we're going to have here are households who experience income shocks and who are not able to fully insure against them. So agents earn some amount ST, which is going to be a random variable drawn from a set of two values, S low and S high. And this variable follows a Markov process where pi is going to be the probability of getting a particular value for st plus 1, and it's a Markov process, so that depends on the value at the previous state. We're also going to assume that pi of s being h tomorrow is going to be higher if your income shock was already high. If we don't have this assumption, then it's not clear that high really is high if it turns out that tomorrow you're more likely to get the low value. Alright, as I mentioned, there is incomplete insurance, and so the only way to save in this world is to buy or sell a risk-free asset. So that is an asset that pays you 1 unit of consumption for sure tomorrow, plus some interest. In addition, suppose A is your asset holdings. There is going to be a limit. So A may not be smaller than some A bar, where this A bar is some negative number. Of course, having negative asset holdings means that you're borrowing, and so this essentially means that there is a borrowing limit. Finally, let psi be the distribution of assets across households in this economy. So we're going to assume that there is a 0-1 continuum of households. We are going to require that in equilibrium, the total amount of assets in this economy is 0. In other words, the quantity of bonds bought must equal the quantity of bonds sold. And you may ask, how is this equilibrium going to be established? Well, there is one price in this economy, that's the price of the asset itself, and so that will adjust so as to make this condition hold. So next, let's look at the households problem. And let's directly start writing it down as a recursive problem. So the household's value is going to depend on their current income shock and on their current asset holdings. Of course, it will also depend on the interest rate. Let's assume that the households have constant relative risk aversion. This will be their current utility, and then they discount the future using a factor beta, and then they will get the expected value of whatever is their shock tomorrow, given whatever asset holdings they choose today for tomorrow, and the interest rates, which we're assuming is constant because we're going to be looking at a steady state. This is subject to the agent's expenses not exceeding their income. So their income is, well, whatever asset holdings they had plus interest, since they earn interest income on their bonds, on their assets, plus whatever income they get today. This may not be less than their spending, which is on consumption and on buying new assets. In addition, they also face this borrowing constraint. Great. And we're going to need a parameter restriction. We're going to assume that if you have the lowest asset holdings and you have the lowest income, you are still able to afford the lowest holding of assets. Otherwise, there would be some agents here who have negative consumption, and of course, that's not going to be possible. So I always like to solve these problems by eliminating one of the variables, and here the consumption will be the easy one to eliminate, so we'll just replace it using this constraint. And let's ignore this constraint for now and go ahead and take the first order condition. Now the first order condition, of course, is going to be that the marginal utility that you lose if you decide to spend an extra unit of your income on buying assets is going to have to equal the expected benefit of doing so, which is going to be the expected derivative of the value function with respect to its second argument. Next, we need to figure out what's the envelope condition, and for that, we just derive the value function with respect to its second argument. And of course, what we're going to get is marginal utility times whatever it is in here that is multiplied by a, which is 1 plus I, and this term disappears. Putting this all together, we end up with the Euler equation, which we obtain by simply putting these two together and making sure that when we write this out, we've changed the time appropriately as so to update it to the following period. Great, so this is the Euler equation that characterizes the household's problem if we know what I is. Question, of course, is how do we compute this problem? And the answer is that first we have to start with a guess for the optimal A prime. And as usual, a good starting guess for all these problems is to assume that the optimum is 0. Then we're going to end up with this as the solution to the agent's problem for any given A. So you generate a grid of values of A and call the optimum that you get from this a star of A for each of these values of A. Next, we know that the Euler equation is this. So for the next round of iteration, you can try using this equation where you have substituted your optimal function for A 2 periods ahead. So then instead of solving this simpler problem, you figure out what the A star is from here, and then plug it in and use that to figure out what A prime is for the A's on your grid here. And of course, then you just iterate. until you've converged to something that you think is accurate. One key reason why this is going to work is that, in fact, you've assumed that asset holdings A are bounded from below by A bar. It's also possible to show that A is bounded from above. This is going to be true in general for models where there is some sort of borrowing constraint, whether it's exogenous, as here, or endogenous. The key to this is to realize that beta, the discount factor, is going to be less than 1 over 1 plus I. This is going to be because, of course, if the opposite were the case, then people would just invest infinitely, which obviously can't be in equilibrium. And given this inequality, suppose there is no upper bound, then we're going to end up with a contradiction. Essentially, note that this is one way to rewrite this Euler equation. This is consumption at date t. This is consumption at t plus 1. If you had no bound on your wealth, then there would be some agents who are so rich that essentially CT and CT plus 1 are enormous, because given their wealth, the income shock would be kind of irrelevant to their existence. And if those two numbers are essentially the same, then we can say that the two sides are roughly equal, and we can divide by these numbers because, as discussed, they're essentially the same. And of course, this fact contradicts this, because with C being arbitrarily high, we could get arbitrarily close to equality here, which contradicts this idea that beta is bounded away from the interest rate. So we know that, in fact, A is bounded from above. And so it means that for any given guess of the interest rates, we only need to look at a bounded interval of values of A. Now, if you compute this model, you will find it very hard to get a reasonable wealth distribution that looks like the distribution in the United States. The distribution in the United States has two features which are hard to match. One is that there's a whole bunch of people who don't seem to save much. The second is that there's some very wealthy people who seem to save a lot. And one paper that tries to address matching the wealth distribution in the United States with all those unusual features is Gadgetti and Denardi, which is a paper that has the additional feature that it allows us to think about a life cycle without having to use an OLG model. And this paper is also motivated by the fact that if you look at the United States wealth distribution, you see that among the super rich, there's a disproportionately large share of entrepreneurs, which motivates them to think that maybe something about entrepreneurship is what makes the top of the wealth distribution look so unusual. So the way they do this is they assume that there are a bunch of agents, and they are subject to two shocks. We'll call them X and Y, where X is entrepreneurial productivity and Y is labor productivity. And the agents choose in each period whether they want to be entrepreneurs or work in the labor market. So before we get to the agents problem, in addition to the entrepreneurs, there is a competitive sector to which agents may supply labor. In other words, they're the entrepreneurs, and next to them there is also the giant production function in the sky, so to speak, which is constant returns and which is a feature of most simple standard macro models. And it has the usual production function, where output is some number times capital times labor. Let W be the wage, and let 1 plus R be the capital rental rate. Then, of course, we're going to have, very quickly solving the problem of a competitive firm in this sector, that the wage is equal to marginal product of labor and this implies that the capital labor ratio is equal to the wage over 1 minus alpha times A, all to the power of 1 over alpha. In addition, we'll have that 1 plus R is equal to the marginal product of capital which in turn also tells us that the capital labor ratio is equal to 1 plus R divided by alpha times A, all to the power of 1 over alpha minus 1. What does this mean? It means that this expression has to equal this one, and that means that if you know the wage, you know what R is. And this is important because this turns out to be useful for computing the equilibrium here. All right, so now we've figured out what's happening in the big production function in the sky. Let's now move to think about what happens to the agents. Let V be your future value with arguments that we'll get to. If an agent now chooses to be a worker, suppose she gets the following: V of W, indicating they've chosen to be a worker. It's going to depend on their asset holdings, so agents are going to be able to save here too, just like with Huggett. And it will depend on their two shocks. They're going to get some utility, and in the future they will get the expected value of V discounted. Of course, V again depends on whatever asset holdings they have tomorrow, whatever their entrepreneurial shock is tomorrow, and whatever their labor productivity is tomorrow, subject to the idea that their expenditures today, which is going to be on assets for the future and on consumption, may not exceed their labor income, which is going to be the competitive wage times Y, that's their labor productivity shock, plus earnings from their asset holdings. And there is also going to be a constraint on asset holdings. In this case, it's assumed that the workers can't borrow. So the workers' problem looks quite a bit like the Huggett world, except that the lower bound on asset holdings turns out to be 0. How is that possible? Well, in this economy, these asset holdings are not going to be risk-free bonds. They're actually going to be productive capital, which we'll see in the next step. So suppose instead that an agent chooses to be an entrepreneur. Then they get to use a production function of the following form. They get to produce goods themselves directly, and let's say the production function is x times k to the eta, where k is capital. So their value function of being an entrepreneur, of course, also depends on their assets and on their shocks. That's going to equal the same What's different is going to be where they get their income. So once again, their expenditures on new assets and on consumption may not exceed their income. Their income is what? Well, it's the output that they produce here minus two things. One, the way this is set up, the entrepreneurs will have to pay for the depreciation on the capital. And two, they will have to pay for any capital that they borrowed. In other words, they get to put their own assets into the production function, but if they want to use more than they have, they will have to pay for it. And again, of course, we still have this restriction. What makes this problem interesting is that the agent may default on any loans that they take out. And if they default, there is going to be some punishment. So let D be the punishment function. We're going to require, in addition, that the punishment, which we're going to allow to depend on the capital, as well as x and y, must be less than or equal to v of e. If it were not, then they would default, and we would not be on the equilibrium path. Specifically, in this paper, they assume that the lender can seize some fraction f of the capital, and in addition, the agent is forced to be a worker the following period. In other words, you're cut out of financial markets, or rather from the ability to borrow for a period. So that means that in their case, D is essentially equal to the value of being a worker, where you are holding some fraction f of the capital, where the fraction 1 minus f of the capital was taken away. Okay? And of course, finally, the agents are making an occupational choice, and that means that V of AXY equals the max of VW and VE. And that's their setup. How do you compute this? You start by making a guess for the wage, and that immediately tells you what R is, as we discussed earlier. And then you can compute the value functions of all the agents iteratively. For entrepreneurs, this is tricky because you have to figure out how much capital they're allowed to borrow. If you're allowing agents to choose from a grid of values of k, then you can see which is the highest k for which this constraint is satisfied, and just rule them out of being able to use any k's above that. And I mentioned earlier that this model has a life cycle. I didn't go into that when I was talking right now about the occupational choice decision, but essentially what they do is they say that agents are either young or old. When they're young, their problem looks kind of like this, but in any given period, there's a probability of them becoming old. And if they're old, then they retire, unless they're entrepreneurs, and they get to earn some social security payments. And so the way they generate a reasonable wealth distribution is, first, the old people get pensions, and so they don't need to save too much. On the other hand, people who are entrepreneurs have this borrowing constraint, and so there's an incentive for them to save up a lot once they become entrepreneurs, because they're trying to overcome the financing constraint. Finally, all of the models that I discussed so far assume a steady state. And so, of course, you might wonder, are there ways of computing models with heterogeneity and shocks? And of course the answer is yes. There's more than one approach to doing this, but a popular one is that of Crucell and Smith. They show several things. One is that having some heterogeneity in discount factors can give you a better wealth distribution, by which I mean one that matches the data better. That I think their key contribution is that they develop methods for computing models with household heterogeneity, and their methods carry over to other forms of heterogeneity with aggregate uncertainty. So what they have is a model where people face employment and unemployment shocks, kind of like Huggett, except that their assets are actually capital, kind of like Gadgetin Denardi. And they face aggregate shocks. So let mu be the distribution of wealth at date t. The key problem, of course, is that this is the state variable of the economy. And so aggregate variables like wages and prices that vary over time depend on mu sub t. Of course, mu sub t follows some law of motion, which depends on a combination of the shocks that are hitting the economy and agents' optimal wealth decisions. And the way they approach this is they suggest that you propose an approximate law of motion from some class of such laws that depend on some moments of mu. Let's say, for example, maybe it depends on the average, or on the average and the standard deviation. Then you figure out which is the optimal such law of motion from this class, and see if it's accurately predicting the prices in the subsequent period when you simulate the model. This is found to be quite efficient and effective in many contexts. So, I hope this brief introduction is useful. Take care, and I'll see you next time.